Yeah.
Just throw laps.
Yeah, just let us know this file.
Okay, and then I have another one that I'm finishing up. Can I get turned in on Thursday?
Yeah, Thursday earlier. All right, let's go ahead and get started. So I think we have to finish up a little bit of chapter 20. But first of all, so I can't say this enough, but check your grades, and check your grades. So I've already heard from like a few people this quarter that, you'll get a paper back and the grade is not in the grade book, so double check all that for me. Especially because I feel like I've been having issues this quarter since Blackboard is all online, and I don't know if it doesn't save or what. But just check your grades. And then the other thing that's really annoying about Blackboard is because I think I have it calculated as a running total. So that means I have to physically put in zeros, otherwise it doesn't count against you. But if I put in the 0 too early and then you go up and make up the work, like for a reading quiz, even if I hit submit, it won't change your grade in the grade book unless I go back and manually say yes, that grade. So it's a huge pain in my butt, but I just need your help. So just make sure that everything has a grade that should have a grade. If you did it and it still says a 0, just let me know so I can manually change it. So I have to manually change everything. So just know that. And so I'm going to be inputting a bunch of zeros to make sure that the grade is correct. And so just watch for that. So again, just check your grades, So make sure you have credit. Not zeros. And so I have a huge pile of work to hand back. So make sure that you get your work so that you can check your grade and make sure everything is accurate. And then, so just a friendly reminder, so no labs this week. We're done with that. We can still have our study powwow session. So that will either be probably in the lab space, we'll just say. So if you need to finish stuff, we can hang out there as a class and work on that and just get stuff turned in. So that's a big thing. So I see papers up there. That's awesome. I'm excited to read them. So make sure you get your paper in ASAP. So if not today, then hopefully by Thursday, that would be ideal. And so today we'll do our review. And then, of course, final on Thursday. Any questions about that? So again, big thing, check your grades, help me out. And I'll make sure to try to get all your papers to you today so you can check your accuracy. All right, so let's finish up the last little bit, which was how to classify these salts as acidic, basic, or neutral. And so let's just read through the block of text, and then we'll break down what it's really trying to tell us. So it says, if the salt cation is a counter ion of a strong base and the anion is a conjugate base of a strong acid, neither ion reacts with water to affect its pH, therefore a neutral solution will be formed. So let's break that down and let's analyze that. So what the heck are they telling us? And so I just like to do this little analysis. So we have sodium chloride. That's their first example. And so let's break this down. If the salt cation is the counter ion of a strong base, so then it's asking, well, what base does sodium come from? So what base involves sodium? So NaOH, or sodium hydroxide. And then what do we know about sodium hydroxide? Strong base, weak base. So if it's a strong base, we know that it fully dissociates. And so what we're saying is, okay, we have this sort of equilibrium. And so that means that our salt plus our water, right, it's unable to form HCl or anything. It can't do anything, so it can't pluck this off. This is no reaction. And so that means, so the salt cation is the counter ion of a strong base. So that's going to be neutral. And so we can put neutral here or whatever. And then the second half of that, and the anion is the conjugate base of a strong acid. So what acid is chloride from? So HCl. So we can do our little analysis. So chloride, it's from HCl. And we can write this fully disassociates, so strong acid. Again, what this is saying is this chlorine can't reform anything. And so our equilibrium lies all the way to the right, so that means this is neutral. And so that explains why sodium chloride then is overall neutral. So if we do the analysis for calcium nitrate, we'd find the same thing. So calcium nitrate, we do our analysis. So where does calcium come from? What base? Calcium, yeah, hydroxide. So it's easiest just to stick hydroxide. So that's a strong base. So that means that calcium is neutral. Where does our nitrate come from in our acid? So nitric. So this is one of our strong acids. So strong acid. And so that makes our calcium and our nitrate neutral. So then we get a neutral salt. And then let's do KBr. And again, I'm kind of trying to rush this just a little bit. So then KBr, same sort of process. So what base does potassium come from? So potassium hydroxide, this is our strong base. So that means potassium is neutral. And then what acid does bromine come from? So what acid? HBr, so that's hydrobromic acid. So this is strong. Strong acid. So again, we have our neutral salt then for potassium bromide. So let's look at our different cases where we won't just have this neutral solution. And so now let's read the paragraph. So if the salt cation is a counter ion of a strong base, okay, well this is the same thing as before. So basically we're saying the salt cation is a counter ion of a strong base, so that means our cation is neutral. But let's go on to read. So if we have our neutral cation, but then the anion is the conjugate base of a weak acid, and so there's our key. So it has to be the conjugate base of a weak acid. Then our cation is pH neutral, so that's what we said, right? Neutral cation then. But then the anion would be basic, so then we get a basic solution. So let's do these again in a little bit more in depth. So now we're looking at sodium fluoride. And we already know they're going to be basic, but we can do our analysis. So what base did sodium come from again? So NaOH. And so it should start to feel a little repetitive. And once you get it down, it should feel good. So again, NaOH, we've seen that before. So this is, of course, our strong base. So that makes our sodium neutral. But now let's analyze our fluoride. So where did fluoride come from? What acid? So hydrofluoric, except, so HF now has an equilibrium. And so now what we're saying with this expression, so fluoride can go ahead and react. So it's going to react, and this is the equation you want to write, because you want to write your salt with water. So salt plus a neutral solution. Now it's going to pluck off one of those H's to give you HF. So it reforms the acid, plus it leaves us with hydroxide in solution. And of course, anything that forms hydroxide means that this is a basic solution. And so now we're showing how fluoride is indeed basic. And so now because of this, we can say that our salt is going to be basic. And again, our anion is a conjugate base of a weak acid. So yes, it will go ahead and reform HF, and again leave you with hydroxide, which is our definition of a base. So anything that forms hydroxide in solution. And so then we say that the fluoride is our basic salt. And so in this case, right, we have a neutral plus a basic. And so this gives us an overall basic salt for sodium fluoride. So again, you dissolve sodium fluoride in solution, and it would give you a basic pH. So we can do that. So let's look at, now this is calcium acetate. So let's see how that's similar and how we would do that analysis. So there's our acetate. So again, perform our same sort of analysis. So we have calcium and acetate. So what do we know about calcium? What base is it from? Is it acidic or neutral? So calcium hydroxide, so exactly, so that means calcium is neutral. So that's what we expect. And so what acid, does acetate come from? So acetic acid, and then what do we know about acetic acid? Is it a strong acid, a weak acid? So if it's weak, then of course we know we have this equilibrium scenario. And so this is in the forward direction, then we want to write what the base is going to be doing. So reacts with water, and so that means it's going to make our acetic acid plus form hydroxide. So there again, our definition of a base, anything that forms hydroxide. And so now we know that acetate is a basic salt. And so if we have a neutral cation, a basic anion, so this gives us an overall basic salt. Does that make sense for people? So this can be tricky, so don't be shy to ask questions. And then let's look at this last one. So potassium nitrite. Okay, NO2. So we do our analysis again. So potassium We already know that that comes from potassium hydroxide. So that's a strong base. So we know potassium is neutral. And then what acid does NO2 come from? So nitric is HNO3, but so if you're losing an oxygen, do you remember how to name that with acids? Yeah, so then it would be nitrous acid. And so nitrous acid does have an equilibrium. So I think this was it was here on this chart. So nitrous acid. And so now we can write the equilibrium expression. And so if we can go back and forth, that means this species will react with water to again reform our nitrous acid and make hydroxide in solution. So there's our base. And so this means that it is a basic salt then for nitrite. And so this means our overall salt would be basic. And so the other thing that you should be noticing with all this, so cations are either going to be acidic or neutral, and anions are either basic or neutral. So now let's look at our next scenario. So let's say, so now we have, so if the salt cation is the conjugate acid of a weak base, so let's go back to that, and the anion is the conjugate base of a strong acid, well, we know if the anion is a conjugate base of a strong acid, then the anion will be neutral. And so in that case, so again, going back to the salt cation is the conjugate acid of a weak base. So now we have conjugate acid for a weak base. We have to figure out what base it came from. And then that means our salt is acidic. And so as you can tell, there's very few examples of this. Since, like I said, well, your cation is either acidic or neutral. But like we've seen, most of our cations are neutral. So this is one of our few acidic cations, other than like metal ones. Well, let's just go through our analysis. So we have ammonium chloride. So if we start with our ammonium, so what base is ammonium from? You say ammonia? I saw your mouth move. So it's from ammonia. And so we can write down, so ammonia plus water forms ammonium plus hydroxide. And again, if we have equilibrium, that means that we can have ammonium plus water. And so water will pluck off one of its hydrogens, reforming our base and then forming hydronium. So making H+ ions in solution. So here's our definition of an acid right there. And so now we can say, yes, our ammonium is acidic. Meanwhile, so chlorine, just a quick analysis. So we know chlorine is from HCl, so that's our strong acid. So we know this is not going to reform. So we can say our chloride is neutral. And so now we have acidic plus neutral. So then this gives us overall acidic salt. So the only other weird scenario well, before I get to that, so the other thing, so you also have like what's called these highly charged metal ions, so these can also be acidic. And so this is kind of your key. So if you get a salt cation and it's charged, kind of like aluminum 3+, and the anion is, of course, the conjugate base once again, that means you have an acidic cation and you'll have an acidic solution. And so glancing at your exam, we don't have this scenario, but the only other scenario where things could get weird is, well, what if you have ammonium fluoride? So that's a strange one. So you know from before, so we know ammonium, right, that's acidic. But we also know fluoride, well, that's basic. So now, well, which wins? And so now it says, so if the salt cation is the conjugate acid of a weak base and the anion is a conjugate base of a weak acid, then the pH depends on the relative strengths of the acid and the base. And so then we have to look at their Kas or Kbs. And so in this case, we want to compare their Ka to their Kb. And so what we do, so let's see. So we have to find their Kas. So we could look up, so HF. This is what we care about. So let's write it down. So 3.17. Or 6.8 times 10 to the negative 4. Or again, our Ka. So that's this reaction. So acid plus water gives our H plus our anion. And then, so now if we want to compare, so now we need to figure out the Ka of ammonium. And then we also need to figure out, so it's asking for the Kb of F minus. So then how do we figure out all this? So this is for HF. And so Ka times Kb is equal to Kw, that water constant. So we can figure out Kb from Ka, and then we just have to figure out ammonium. So unfortunately, ammonium is not on our chart, so then we have to ask Google. And so let's ask Google. And so we could just look up pKa of ammonia. So then you want your Ka, so this is your strength of your acid species. So this is either, so pKa, and so I just Googled the pKa of ammonium, but I want to show you some things. So that's one way to get it. But then you might ask, so what's the pKb of ammonia? So we could do 14 minus 4.74. And so this also gives you the pKa. They could have also given you, so don't forget, right, you could look up the KB of ammonia. That's the same thing. So my whole point is there's a lot of ways to get the same answers. If you have the PKB given to you, then you can type in, negative log of 1.8 times 10 to the negative fifth. So that gives us back, right, our PKB. And so that's the base direction. Then again, we can take either 14 minus the pKa, or if we wanted to do our Kw, it's the same thing. And then negative log of this to get back to Ka. So now we got back to that pKa of 9.26. So that's how to go from pKa to pKb, all back and forth. And then, so we're still trying to figure out who's stronger. So we're comparing, again, we want the acid, the Ka of our ammonia versus the Kb of our fluoride to figure out who's stronger. And so let's figure out what the Kb is. And so we said that this is the Ka for HF. We can figure out the Kb. And you could have also asked Google. Google would have probably told you an answer as well. Oh, sorry. Divided by 6.8. So that's our Kb. So 1.47 times 10 to the negative 11. And I like comparing their Kas so you can kind of see the exponent easier. But if we're comparing, so that means our Ka was 5.56 times 10 to the negative 7. Or sorry, negative 10. And so ammonium, it has a slightly larger pKa value than our Kb of fluoride. And so that means that our solution will be overall acidic then, since this is slightly stronger. So now I'll just rewrite that. So our Ka was this 5.56 versus the Kb of 1.47. And so this is larger, so that dominates. Yeah. Which one? Sorry. So that one, we said, sorry, now I forgot. So I think the easiest way to start with, if you looked up the Kb of ammonia, you could get this answer, 1.8 times 10 to the negative fifth. And then I just divided it here. So our water constant, 1 times 10 to the negative 14, divided by that gives us Ka. But I think you could also, Ka of ammonia. And so if you Google it, it also tells you. I'm just showing you how to get it, because sometimes if you Google it, like it doesn't tell you, or I don't know. Or, on an exam, let's say you were given like a made up acid and you couldn't just look it up. That's how you could calculate it. Yeah.
For clarification, so when you're comparing two acids, the one with the lower pKa of the right, because it's an inverse.
Yeah, it's kind of weird. So yeah, the lower the pKa, the stronger the acid. And that's why I like writing it in the exponent, just so I don't get confused myself. All right, let's do this really quickly. So take a few minutes and determine whether these are acidic, basic, or neutral. I think this is a tricky one. See if you can figure out what it's derived from, and then we'll go over it. And while you do that, I'll try to hand back some more papers. Yeah. Yeah. All right, let's go over these. So strontium chloride, acidic, basic, neutral. Don't all answer at once. So what do we think about strontium? Do you think that's acidic or neutral? I think I heard someone say neutral. So yeah, strontium comes from strontium hydroxide, so that's our strong base. So strontium is neutral. And then what about chlorine? What do we already know about chlorine? What acid is it from again? So good old HCl, so we know that that means our chloride is neutral. So this is overall neutral. What about aluminum bromide? What do we say about those aluminum salts? Oh, what did you say? Acidic, so perfect. So aluminum was one of those special cases, and so aluminum tends to be acidic, although it can also act as a base, so sometimes you'll see aluminum as like amphoteric. And then HBr is, of course, a strong acid, so that means bromine is neutral, so overall acidic salt. What about this one? Can you name that? Or do we have a guess? Acidic, basic, neutral?
Methyl ammonia nitrate.
Yeah. So methyl ammonium nitrate. I like that. And so if you didn't see that, just try to recognize what groups are there. So right away you can kind of see this nitrate, and that leaves you with this thing. And so let's do, so our nitrate analysis, we already know that is neutral since it comes from our nitric acid. But then what about this methyl ammonium? And it might be easier if we write it out so we can see what it looks like. And so what does it kind of remind you of? What has that same structure? And I didn't put a charge on it, but I should, right? Because if this nitrate has a -1 charge, this methyl ammonium has a +1 charge. And so what does methyl ammonium look just like? Or think more simply. What's our acidic cation usually? Yeah, ammonium. So it looks just like ammonium, right? So ammonium's, the only difference is that instead of that methyl group, it has an H on there. And so we would expect it to behave the same way. And we can also write down the reaction of what's going to happen. And so let's look at our methyl ammonium in solution and write what happens with water. So just like with our ammonium, this can go ahead and lose our hydrogen, so then we make hydronium in solution. And then if we pluck that off, so then that leaves us with this little guy. And then does anyone have a name for this guy? You did great on the methyl ammonium. So then this would be methyl, and this is an amine group. So this is methylamine. And then, did any of y'all watch Breaking Bad? So do we know what methylamine is now? So if you didn't watch Breaking Bad, there's an episode where there's like a giant tanker car of methylamine, and they go and like steal it and hijack it. And ever since that episode, methylamine became an extremely regulated substance. So good luck ever working with methylamine again. But yes, this is, again, another way to make meth. So what have you learned in chemistry? How to make meth. Perfect. But we've also can see from here, so an amine, these tend to be basic. And so that means that, once again, just like our ammonium, our methyl ammonium is derived from our weak base, methylamine. And so that was a long way to answer that then our methylamine is acidic, so CH3, NH3+. And so this would be acidic, since it came from our weak base, methylamine, and so this is overall acidic. And then what about D here? What acid did it come from? Acidic, basic, neutral. So what do we know about sodium? So is sodium acidic, basic, neutral? So here, a neutral. And then, so we can always go back here. What the heck is a CHO2? And so this is kind of helpful. Oh, that's probably formate. So that's from formic acid here. And so we could write out our formic acid equation. So we know that makes our acid plus formate. And since it's weak, we know our formate can reform our formic acid in solution, leaving us with hydroxide. And so that means this is basic, giving us overall basic salt. And then this last one, we'd already said that it was acidic due to that ammonium having a stronger Ka than the Kb of fluoride. All right, questions about the salts and all that? So let's at least touch on titration. So blah, blah, blah. I think y'all know how to do titrations. And kind of what you can see, so if you have a strong acid and a strong base, just notice how much that titration curve jumps. So you were super low, and then you have your equilibrium, your equivalence point. And of course, you guys had tons of fun with that and seeing how quickly it turned pink. And so that's why your solution too goes from like light pink to dark pink super quickly, and why it felt like it was, really difficult maybe to get that true equivalence point, since it's really sensitive. And then so you have a weak base, you can tell that's a little gentler of a slope here. Same thing, weak base versus strong acid, so not as extreme. And then if we were doing a polyprotic acid, so you have several equivalence points then depending on how many protons are there. So with this acid, we have 2 acidic protons, so then you have 2 equivalence points. And then the other last little bit is just about these indicators, but I think we kind of know how indicators work. And other key points might be, so if you were doing like a polyprotic acid with several endpoints, you might want to use like thymol blue, which has a wide range that goes from red to yellow all the way to blue. Or of course, this one, alizarin, might be another good choice. But people tend to use thymol blue for larger titrations. Or of course, you'll use like a digital pH meter. That's the other way. All right, let's move on to review.
How do digital pH meters function?
You calibrate them. It's like based off of some sort of voltage difference that it reads out, and then you do like a 3-point calibration, acidic, neutral, basic, and then it just measures it digitally. All right, so looking at your exam, start off with some multiple choice questions. Let's do some practice. So let's say you're given that your rate is equal to K times A squared times B. So what is the overall order of this reaction? So just take a minute or two for this one. So what's the answer to number 1? So what's the overall order of this reaction? So remember, you got to add up all of them. So third. So remember, for the overall order, you just add up all the exponents. So in this case, 2 from A, 1 from B to give us 3. So now looking at the next one, we have 2AB plus B2 gives us 2AB2. And then we're given our rate is equal to K AB squared times B2. So what happens to our rate if AB is doubled? And then all these are in a gas state. So then we can also ask what will happen if you increase the pressure. So take a minute or two for those ones.
Did he say
They should be.
that?
Yeah, there's a pen on the other one, but double check that they got entered. All right, so what happens if AB is doubled for our rate? I thought you were raising your hands here. What? You should be able to answer this. So AB's doubled. We're going to put you on the spot. It's AB squared, right?
I'm probably wrong, but would it be quadrupled?
Quadrupled, exactly. I can't spell quadruples, but perfect. So our key point, so if it's squared, and then we double it, so times 2, so 2 to the 2, so that gives us our 4 times. Excellent. And then, so what will happen then if we increase the pressure? Any thoughts? What did you say, sorry? What will increase? And in which direction will it go though? Left, right? So you're right, so rate will increase in what direction? So go to the right. And so how do you determine that? You're correct. And so in case you didn't hear, so less gas molecules, so I said they were all in the gas phase. And so our product only had 2 gas molecules versus 3 on our reactant side. So if we increase the pressure, it's going to want to alleviate that, so it's going to shift to the right where we had less gas molecules. And then, so other things, just to review for your multiple choice questions, I don't want to give it all away, but just like factors that influence reaction rates. So of course that's like temperature, concentration, and pressure, and of course number of collisions. And the number of collisions, all that's related to is how much energy they have, and of course what orientation they're in, and of course frequency of productive collisions. All right, so let's do some more problems. Yeah.
If you were to decrease pressure, would it need to go left?
Yes. So then in this case, right, we decrease pressure and want to get back to that pressure, so we would favor making more reactants to make more gas molecules. All right, let's try this one. So we have AX5, which is a gas, gives us AX3 plus X2. All those are gases. And we have our Kc is equal to 0.0511. And so we assume we have a 1.5 molar concentration of our starting material. So what are our equilibrium concentrations? So I'll give everyone a few minutes to work on that. So everyone should have gotten back all the papers that I owed them. All right, how's the algebra going on this one? So I'm just going to write our setup really quick. And so in this case, right, we only had reactants. So that at least told us what direction we're going to be going in. So we have to go in the forward direction to the right. So then our change will be minus x plus x plus x. And so that should have given us something like this for our equilibrium. And then so we could set up, so Kc was equal to that number, which is equal to products over reactants. So then we got something like this. And then, do people want me to do the algebra? Oh, okay, mixed responses, but I'll do the algebra. And so at this point, it was just algebra, so I multiplied everything by the bottom. Give me x squared. And I'm just trying to rush it a little so we could get through all this problems. Oh, come on, why'd you do that? So then you should have gotten something like this. And then from here, it's just moving it over to one side and doing the quadratic. Equals 0. So then quadratic, which I think ended up being something that looked like this. Squared minus 4ac. Let's see, I have my value for x. I don't have the other values. So you should have gotten 2 values for x. I only wrote down, I guess, the relevant one. Obviously, so if you do negative minus something, that's not going to be a good value. So did we all get x is 2.52? So I see some nods with that. And so if x is that, that gives us, so that means our x2 concentration is 0.252, AX3, 0.252, and AX5 is 1.5 minus our answer. So I get 1.248 or 1.25. Questions about this one? Okay. No questions. So let's try our next sample problem. So now, what is the pH of a 2.3 molar solution of phenol? And phenol has a Ka of 1.3 times 10 to the negative 10. So do we have answers or? So we can at least start with our reaction. So there's phenol. And so this is just our conjugate base species. And of course, this is HA. Oops. And so initially, our initial concentration is at 2.3 molar of our acid. Then change. So again, we only have reactants, so we can only go to the right. And we get our equilibrium. So 2.3 minus x, xx. And then from there, we can just plug it into our Ka. So you get something like this. And so did people solve it with the quadratic, or you could have also made an assumption here. Since this is tiny, we could try our 5% approximation. Since this is fairly large compared to this 10 to the negative 10. So for an exam, just saying, right, this is a good setup point, because then from here is just algebra. So you could have asked your calculator to solve it. I'm feeling lazy, so I'll just assume less than 5% and then check that method out. You could go the quadratic equation, that's also perfectly fine. So then if I make my assumption, and I go ahead and solve for x, so times 2.3, so then I just need to take the square root of this. And so I get x is about 1.72 times 10 to the negative fifth. And then, so the first thing I want to do if I'm running with this 5% assumption is to check that. So divided by my initial concentration, so of course times 100. And yep, that's smaller than 5%. So it was fine to make that assumption. So check. And our pH then is just our negative log of H plus concentration. So then we can just plug it in. So I get a pH of like 4.76 roughly.
I did the quadratic route, and that's also what I got.
Excellent. So 4.76. So here it worked by quadratic. Caitlin, did you stick it into your calculator and it spat it up? Oh, you did? Perfect. I was just curious what you did. Sweet. Any questions on this one? Yeah.
So how did you know you could do the 5%?
It's all based off of this equilibrium constant. So this one was super tiny to the negative 10. And like, you know, if I had given you chlorous acid though, I probably wouldn't make the assumption, right? Because that's 10 to the negative 2. That's a little bit closer. So there you would have to divide this divided by your 2.3, or whatever you get for x, I mean. But just looking at like your order of magnitude, like that one would be cutting it close. Even the nitrous is probably cutting it close. We'd have to, again, do the math to see. But then once you're at like, -8, -10, whatever, you can tell, well, that's going to be too large of a difference, so it doesn't matter. And you can always like make the assumption and then check it, and then as long as it works out, then you're fine to just move forward. And then if you make the assumption and it doesn't work, then you just need to solve it more explicitly with the quadratic or whatever. Let's try another sample problem. So let's say we want to figure out what our Kc is for this expression. So we have 4a plus 2b gives us this 2a2b. And I do know my Kc for these other equations, so I know that a2b plus b gives me a2b2, and that has a Kc of 2.22. And I also know that 2a plus 2b gives me a2 b2. And its Kc is 10.5. So see if you can determine this Kc. So how are we doing on this? Any thoughts or? First of all, how do I even add up these two equations to give us the top one?
The first equation, reverse it. A2, B2. I would also times it by 2.
The first one? Okay, so then times, sorry, I was slow. So 2.22, so let's do the -1. And then we want to, you said double it, so times 2. So 2A2B2 gives us 2A2B, is 2B. So now this is 2.22 times the -2 power, since we inverted it and doubled it. All right, and then what about this last one? What should I do? So double it. So 4A plus 4B gives us 2A2B2. And so this would be 10.5 squared since we doubled it. Now, does adding these two give us our top equation? So yes, and we can go through it. So let me zoom out. Let's see. So I have a 2B, but then a 4B. So this becomes 2B. And then, so 2A2 cancels, 2A2 cancels. And yep, so that looks good. 4A plus 2B gives us 2A2B. Perfect. And so now what's the last little step I have to do to figure out my KC? So now multiply these two values. So that's why I was trying to be careful. So we know what we did. And so now we just have to take the 2.22, take that to the -2 power, times 10.5 to the second. So I get like 22.37 or so. So I get some more confirmations. Excellent. So I get nods from people. Yeah, so you multiply these two at the end. All right, I'm going to give you probably the last two problems because we're out of time. And I don't know if people just want to stay and go over them, or if you have to leave, you'll at least have the problems. So it is second order in A with a rate constant of 2.8 times 10 to the -2 seconds at 75 degrees Celsius. So how long to go from an initial concentration of 0.97 molarity to 0.27 molarity? And then the other question that's on your exam that we haven't gone over that I want to give you is, so the rate constant for a first order reaction is 4.4 times 10 to the negative 8 at 25 degrees Celsius. So what is the rate at 50 degrees Celsius if the activation energy is 1 times 10 to the 5th joules per mole? And just giving you the R is 8.314. All right, so those are the last two problems. If people want to stay and work on them, I'm more than happy to go over them. Otherwise, if you have to leave, I understand. Oh, I think I sent it to you this morning, so double check it right now, because I forgot to do that. But if you still don't have it, then I'll resend it.
Also, I let myself get way behind this quarter, and I just wanted to know, is there any, like, things that I should specifically prioritize getting done? I'm working on getting a lot of lab write-ups done. Is that the most important thing to do?
Probably if you're missing a bunch of labs. I can't remember. I want to say I dropped the lowest lab, and I'll drop probably the lowest 2 quizzes, so that gives you some leeway. But
On the earliest day, I'm not going to meet for class, but I'm taking my math final, I'm just using the gap between math and chemistry, but me.
all right.
Just got diagnosed with ADHD, so that explains a lot. So
Yeah.
Okay.
Finally trying to learn the coping skills around like homework and so.
Okay, so we have a question about this question. So if some of the hydrogen leaks out of the hole, the volume of hydrogen goes down.
Yeah, so that means moles of hydrogen goes down.
Right. So when the volume of hydrogen goes down, so like you can use these two as an example, the moles of hydrogen and the moles of magnesium both go down. So magnesium would read 2 well.
But you're dividing it by a smaller amount. So if it is divided by a smaller amount,
But it's a mole to mole ratio.
right? But then you have to divide your grams of your magnesium divided by moles of hydrogen. So if you have less moles of hydrogen, then you're dividing it by a smaller moles. So then that gives you a bigger atomic weight.
I feel like that question is kind of misleading because here it says moles of hydrogen in the tube and therefore moles of magnesium.
Yeah.
I see. I feel like that was a hard question.
No, a lot of people got it wrong. All right. Sounds good. Probably PowerPoints and then like doing the sample problems.
The sample problems,
Yeah,
okay, that are
probably
in
like
the
the-
textbook?
Or
the
like
ones
what
that are
we,
on the PowerPoints?
like the ones that we went over,
Okay.
and then like the quiz problems.
Okay.
Yeah, that would be a good start.
I like it.
All right, question? Sorry, where? Rate constant of 2.8 times 10 to the negative 2 seconds. At how long to go from 0.97 molar to 0.27 molar? The rate is 4.4 times 10 to the negative 8. What is the rate at 50 degrees Celsius if the activation energy is 1 times 10 to the 5th joules per mole? All right, did we get a chance to at least attempt the first one?
I'm too busy arguing with you, sorry.
So do we have a formula for this one maybe? Or setup at least? Or your formula sheets? Yeah. I see one formula sheet. I personally still need that formula sheet, so. Yeah, we'll just move on over to the lab.
Would it be the 1 over the AT equals the KT plus A over?
Yeah, equals KT plus 1 over A. So that looks good. And then we could rearrange this to give us 1 over AT minus our initial to give us KT. And then plug it in. So remember, setup goes a long way. And then they gave us K already, so we didn't have to use half-life to solve it or anything. So we can just plug it in. Does anyone have the answer punched in? And then did we get like 95.45 or something? So I see at least one nod. So 95.46 seconds. Questions on that one? And last one. So see if you can set this up. I just have to run to the bathroom because I have too much coffee, and then I'll do the math. So do we have a formula for this last one? Probably want something like Arrhenius 2-point, sounds like. And so I use the natural log of K2 over K1 is equal to our activation energy over R times 1 over T1 minus 1 over T2. And I saw this in your labs where people plug Celsius in instead of Kelvin. So don't do that. So make sure, right, temperature is in Kelvin. And that's really, I think, the hardest part. So let's see. So this is 298 Kelvin. And what's 5323? Somebody help my mental math out. Oh, 50 degrees Celsius is perfect. I just want to double check before I did all the math. And so we're trying to find K2. We have K1. We're also given our activation energy, so that was nice. And it's in joules per mole. And so just in case, right, if they've given it to you in kilojoules, make sure you convert it back to joules. It's based off of your gas constant, which is in joules. So all that should work out. And then so T1, 298 minus our T2. And so now we just have to plug it in and solve. So I would start with just the right side, calculating that. Then I get something, the natural log of K2 over this is equal to 3.124. And this is where we can take everything to the power of E. So you get rid of the natural log. So then you get K2 over this is equal to whatever E is to this power. So 22.737. And then multiply everything by the 4.4. Yeah, 737. And multiply it by the 4.4 times 10 to the negative 8. And that should give you your new K2 of like 1 times 10 to the negative 6. Any questions on that last one? And so looking at that, that covers your exam. So like I said, it's going to be 5 multiple choice questions, and then, so 6 is a rate constant one, 7 is just like this one, 8 should look pretty similar to this problem, adding two equations together. Then there's a pH question that should resemble that one, and then some question that resembles this one. And that is it. So 1, 2, 3, 4, 5 free response, 5 multiple choice. And we went over all the types of math problems. We'll see.
Can we go back to the math on the one with the 3 equations to find the case? Yeah, I just wanted to double check the math.
All right, I'm going to go ahead and stop the stream for now. So thanks if anyone's watching online.